Yeah, okay, so I'm Jules, and I'm a student at NUS, and I primarily like math and yeah, so I like math and programming languages, but in Singapore it's kind of hard to find a job that specializes in like abstract algebra or like programming language, so I'm okay if anything. So Artfuscator, I will need to go through some background in order to talk about what this project is. So a very quick primer to how programs work in case like y'all don't know. You start with like some kind of code, which is like in this case it's a C program, and it gets compiled into machine code, which is like a bunch of binary. And this binary will be executed by the CPU. So reverse engineers are people who read the machine code to understand the binary's functionality. And this is a fairly important job, and it consists of people who are like malware engineers, software crackers, vulnerability researchers, and masochists. Yeah, but reading a program's binary is almost impossible because it's not human readable. So reverse engineers utilize a very high level and human readable language known as assembly. And so they disassemble a program's binary into something that's somewhat readable. And also they have like a suite of tools to help them to read more code. And a very popular and extremely expensive one, which nobody pays for, is it's $800. Nobody pays for that. Is IDA, which is short for Interactive Disassembler. And it has a very useful functionality known as the graph view. And the graph view is primarily used to inspect control flow. So for instance, like you look over here, right, it's kind of hard to see, but there's a branch over here. This means it's an if condition. Unfortunately for reverse engineers, their job is a cat and mouse game because bad actors and shitty companies want to keep making their software harder to reverse. So as a result, reverse engineers are forced to deal with monstrosities like this. This, and like this. This in particular is something called control flow flattening, which is horrendous. Like you don't want to see this in your job. So reverse engineers are trained to endure higher and higher levels of like psychological torture. So that's where my project comes in, Artfuscator, because Artfuscator is a novel approach to psychological warfare against reverse engineers. It's like it offers a radically new experience. Yeah, so instead of looking at like this control flow, it looks like shit. Why not look at this, right? So Artfuscator is primarily a C compiler, and it compiles a C program into a single control flow graph arc. So for instance, here you have like hello world, and then it gets compiled into this, which is very nice for anybody who wants to reverse it. So you might ask, like, why in the world would I embark on a project to make reverse engineers' lives even harder, right? And the answer is because of COVID. So I'm not the first person to come up with this idea actually. So there was a previous project called REPsych by Christopher Domas, and it is the first project to create control flow graph art. So Christopher Domas is a pioneer in psychological warfare and reverse engineering. Like he was the one that created the flagship DEFCON talk on psychological warfare, and he invented control flow graph art. However, his project has a fatal flaw, and the fatal flaw is that the graph it generates, it looks like an image, but it has no functionality. So any competent reverse engineer will realize that they do not actually need to reverse the graph. So it kind of defeats the purpose of the psychological technique. But Artfuscator fixes that because the entire program's functionality is encoded into the graph. So now I can go into like Artfuscator internal, which is what you are here for. So let me just say that Artfuscator is a monumental achievement in compiler engineering. But it is built on a world of giants. So Artfuscator, first and foremost, is built on an intermediate language called ELVM, and it's a very simple intermediate language with only 10 instructions. And ELVM, on the other hand, is built on 8cc, which is a tiny C compiler, and it's a very hackable C compiler. So ACC is written by the very famous Ray 314. If you don't know this person wrote LD, the canonical linker, and he also wrote one of the fastest linkers in the world, which is Mode. And this guy, I don't know what he does actually, but like he compiled C into brainfuck. So, and then there's me. Yeah, I wrote Artfuscator. And so here is the credit breakdown of Artfuscator. As you can see, like I deem my technical contribution as very tiny compared to Ruins and Shins. And in case you couldn't see it, here's a zoom picture. So in more detail, Artfuscator starts with the C compiler ACC, and ACC implements like the Lexer, parser, and codegen. So it converts C code into a bunch of tokens, into an abstract syntax tree, and finally into x86 machine code. And ELVN removes the codegen from ACC and implements their own codegen, which outputs their own architecture, ELVN. Finally, Artfuscator consists of my own codegen, which takes in an ELVN program and outputs art. So in other words, the only component for Artfuscator contributes to is the codegen. That's the only thing in Artfuscator. And the job of the codegen is to convert an ELVN program, which has 10 instructions, as you can see here, the usual move, add, blah, 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 into a cube control flow graph. Which sounds pretty simple because there's only like 10 instructions. But there's a big problem, because if you want to draw using the control flow graph art, we cannot let the program's actual control flow interfere with our art. So for instance, like this kind of branches, we cannot have it because it will destroy the art. So do we spend hundreds of hours to craft the perfect pass to perform like crazy code transformation to remove all the control flow? The answer is no, because we can just trick the disassembler into thinking there's no branches by using core to represent all jumps. And it works because these assemblers don't actually cut off a block when they see a call, and this is for readability purposes. So here's an example. Over here actually implements a jump, but it doesn't look like a jump because the block is not being cut off. And so you can see how it works. It first sets like some register to say where to jump to. Then it actually calls itself, so the control flow goes all the way back up here. And it pops the useless return address that was introduced from the core instruction. And then it looks up the address from an array, but it's an obfuscated address. So it has to deobfuscate the address, and then finally jump to the correct location. So the reason why we need to obfuscate the address is because if we do not do so, either it's smart enough to know where the jump target is, and it will actually draw an arrow to the jump target, which is not what we want. So we need to obfuscate the address. So the result of converting all jumps to calls is that we end up with a control flow graph with no jumps at all. So for instance, like here is a list interpreter, and here is the control flow graph, just one line. So once you have one line, you have limited all control flow. We can now focus on shaping our control flow graph. So we start with a straight line code sequence, and then we cut it up into pixels, and then we can rearrange the pixels, and we can adjust the brightness of the pixel according to how big the block is, right? And then we just connect it with a bunch of jumps. Yeah. So here's the final result. We have the list interpreter, and then it outputs this thing. So I'm going to, okay, yeah, some project information in case you want to know more. If you want to know more about this project, you can look up the GitHub where this is hosted, which is GitHub. Or you can search Artfuscator. It has 900 stars. I'm sorry, it has 800 stars. So it will just show up on Google. And you can scroll down in the README to see everything you need is in the README. Yeah, so last but not least, this project is licensed under the MIT license, which does not hold me liable for any claim damages, psychological damages, or other liability arising from the use of this project. Yeah, so it's demo time. I'll need to unshare my screen. All right. No. Yes. Okay, so we have the list interpreter. I don't write any other thing but these interpreters. And it works as you would expect. So for instance, let's do a 1 plus 2. It works. Oh yeah, fair. 1 plus 2. And we can disassemble with IDA, which is something I totally pay for. It's the pro version, by the way. Yeah, this is going to take a while. Yeah, so as you can see, right, the entire program has one function. So it should be pretty simple to reverse, right, since there's only one function. And we can display the graph. It will take a while. Yeah, so yes, it's safe, it's safe. Yeah, so that's it about for me. So do you have any questions?
That was amazing.
Or you can note down my email.
Is that the student number?
Yes, that's my student number.
Use friendly mail.
Huh?
Friendly mail. Use friendly mail. You can change your thing to like a.
Oh, you can. I was in CHS.
No, it's over there.
Oh, okay.
Yeah. So mine's like two characters. And yours doesn't do any validation, so mine's like 3 characters and then you learn USBT.
Oh, interesting. My LinkedIn is like 10% complete. But yeah, I can self part my website. Yes.
Oh, just show your GitHub.
Oh yeah, my GitHub.
Show GitHub, I'm ready for the Jules.
If the line is recorded,
So now share. Wow, God, fast game, yeah?
yeah.
Oh yeah, this is wrong. I'm year 2 now, by the way. I graduated by 1 year.
To do.
I to do what?
To do that.
No, yeah, you need to we need to do. It's part of it to do this.
Eventually, yeah, I need to fix this typo as well.